This is our second video on the time value of money. And we take our time to solve some problems here in this video. The time value of money is a tool used by the financial industry on a daily basis. Accounting departments as well, of course. There are so many things driven by the use of this concept, time value of money. We start with I'm going to start with sharing a slide with you where we cover what's called the 3 rules of time travel, or these are time value of money rules. First rule being that only values at the same point in time can be compared or combined. We cannot take a dollar today and successfully compare it to a dollar that might be received in the year 2025. The purchasing power of a dollar today might, yesterday I bought an avocado for $1. In the year 2025, I'm unlikely to be able to buy an avocado for $1. At that point in time, I might receive 7/10 of an avocado. So we cannot take a dollar today and compare it to a dollar 5 years from now. Nor could we take a dollar that might be due us in 7 years and compare that to a dollar today. We need to compensate for the fact that there is a time value of money over time. Money moving forward invested will grow. If you had a balance due you multiple years from now and you wanted to know what it was worth today, you would need to discount that amount to a present day value. So rule number 2 is to move a cash flow forward in time, you must compound it. So a present day amount placed in an interest-bearing situation will grow in time and will grow on a compounded basis. Dissimilarly, we have rule number 3, where to move a cash flow backward in time, you need to discount it. In other words, to take a future value amount some years down the road and relate it to what it would be in terms of today's dollars, we need to discount that amount in order to present value it. So to go forward in time, we would use the future value function to compound something. To move from the future back to today, we would use the present value function in order to discount it. I want to move to a graphic that shows this, I think, quite well. And that graphic is found here, where this is called the composition of interest over time. So moving from left to right, we're moving out into the future. So the bottom right-hand section of this slide is the present day. It's labeled as year 0, where we have $1,000. As we move out into the future, we earn interest on that money. That's represented by the green as you move from left to right. Because compounding represents the earning of interest upon interest, each one of the green bars shown in this graph also earns interest. So both principal and interest are earning a rate of return as we move out into the future. And you can see the compounded effect is the difference between the green bar and the sort of teal-colored bars. The teal-colored bars take us to a much larger result. This actually represents $1,000 growing for 20 years at a rate of 10%. And the result is that we end up with a balance. I think that's the correct amount. It is. It's $1,000 being earned for 20 years, compounding over 20 years at 10%. Gives us an answer of nearly $6,800 or $6,720. Let's see what the exact answer is. $6,727.50. So that's what's represented graphically here. You could take $1,000 over a 20-year time period, compounded at 10%. You're going to get $6,727. Or we could start on the far right-hand corner, the upper right quadrant here, and be given an amount that's due you in 20 years. You know now that you're going to receive in 20 years $6,720. What is that worth today rather than waiting for 20 years? You have a contractual arrangement where you're supposed to receive $6,720 odd dollars 20 years from now. What happens if you want to settle that today? Well, you can discount all those dollars. Rather than waiting 20 years, you can accept the $1,000 now if the interest rate environment is at 10%. I need to move to a different set of slides. And we will try to solve some problems. So please have Excel open. And we're going to start by taking $10,000. These are two examples. On the left-hand side, you have an example of placing $10,000 in a stock portfolio that's going to return 12% per year for a 10-year time period. What will be the result at the end of the 10-year time period? Well, you're going to take the $10,000 as a present value amount, grow it into the future. The question is, what do you have in the future? So we solve, given a present value amount, we solve for the future value. So open Excel, and utilizing the FX function or the financial formula function, input FV, or search for the future value formula. You're going to get a drop-down box. In terms of the rate, I'd like for you to input 0.12 because we're going to grow this money at 12%. The numbers of periods will be 10 or 10 years. The present value amount that we're starting at is a negative $10,000. Excel requires the negative value. And you solve. You're going to get an answer which will be $31,058 if we've done it properly. Now, the second example is in bonds, where we would be growing $10,000, 10 years, this time at 8%, which is quite realistic. The fact that bonds are going to have a return significantly less than stocks. How do we know what we'll have at the end of a 10-year time period? Well, we solve for future value. So again, accessing the future value formula, we input this time a rate of 0.08 because our return annually is 8%. We want to compound for a 10-year time period, so the numbers of periods are 10. The present value amount, or what we start with, what we know today, is a negative $10,000. Solve for our answer. And we should end up with our investment in bonds having grown to a balance of $21,589. The reason we contrast these two examples is to show you that at a higher compounding rate of 12%, we were able to grow over a 10-year time period $10,000 to an amount of $31,058. With a lower compounding rate of only 8%, we again saw a significant increase in our balance from a present day amount to a future value amount of $21,589, but it's significantly less than what occurred at the lower compounding rate. This slide shows us what happens in the background of Excel as we use the Excel formulas to solve for time value of money problems. In this case, we took $1,000 as a present value amount, earning 10% per year. That's our compounding at 0.10, or the rates at 0.10, for the number of periods being 5. Then we would end up at the end of year 5 at $1,610.50. The detail shown here, the end of 1 year, end of 2 years, end of 3 years, end of 4, shows you the compounding that occurs in the formulas driven and embedded in the Excel program. Similarly, if we were given a future value amount, knowing 5 years from now you owe $1,610.50, what could you settle that for if you wanted to settle this balance today? Given an interest rate environment of 10%, we would discount the $1,610.50 over 5 periods at a rate of 10%. So using the present value function, or PV, input as a rate 0.10, the numbers of periods being 5, and the future value amount negative $1,610.50, and you will find that the answer is $1,000. What you don't see is all of the detailed calculations that Excel has embedded in it. I want you to use Excel. You could go to the tables, and I'll show you examples of tables in a moment. You could go to the tables, but if you're in the workplace, you'll be required to come up with answers promptly, quickly, without error. So I want you to use tools like Excel or financial calculators, but Excel is the way to go, in my opinion. But in the background, formulas are embedded in Excel that drive the result of these calculations. So let's see, this is slide number 8. I want to move to slide number 10. What are some time value of money questions? Well, you can ask, how much money do I need today to pay you $1,000 1 year from now? We can use time value of money to solve that problem. If I invest $1,000 now, what will I have in 5 years or in 10 years? If $1,000 is deposited each year for 5 consecutive years, how much money will we have accumulated after 5 years? That's a little different. We have a repetitive dollar amount for each of 5 years. That is an annuity, and you'll need to understand the definition of an annuity, which we will get to shortly. If I expect to be paid $1,000 a year for 5 consecutive years, what is today's value of these future payments? That's also an annuity that we would solve for. So what are the things we need to solve these problems? We need to know the interest rate. We need to know the principal amount, which is either a present principal amount or future principal amount. We need to know the time periods. And if we're working with annuities, we need to know the payment stream or amount that recurs. Some typical terminology: the principal, that's the face amount of a deposit or a debt. The time, these are the number of periods, oftentimes in years, but can be in months as well. Could be actually in days. We're not likely to do a daily problem. We're likely to do problems that are in years or months. The interest rate, that's the compounding factor. It's either, if we're borrowing, it's the cost of money. If we're investing, it's our opportunity to grow the money. Compounding is to calculate interest upon interest. Discounting is taking a future value amount, bringing it back to the present day by tearing it down or removing all the compounding to bring that back to a present day amount. An annuity, something you need to be familiar with, is a series of periodic cash payments in equal amounts that occur a set number of periods. Moving ahead to an example. How much money do we need to invest today at 10%, at a 10% interest rate, compounded annually, if we need $1,331 in 3 years? So what is this $1,331? You're given here a future value amount. So if you're given a future value, it's likely the word problem is going to ask you to use or require you to use a present value function. And in fact, if we want to find out what we need today at 10% interest compounded annually, if we want to get to the $1,331 in 3 years, we're trying to determine what's the present value of that future amount of $1,331. So we would use the PV function, accessing under the FX function in Excel towards the top or across the ribbon, you get financial formulas, and access the present value formula, you get a drop-down box. To solve this problem, our rate is going to be 0.10. The numbers of periods will be 3. The future value amount is going to be negative 1331, and we solve. Having done that, you will get the answer of $1,000. I think our next this slide shows you graphically what an annuity is. It's the same dollar amount, so these stacks of dollars are equal. Multiple periods, the same dollar amount. That's an annuity. I happen to be the beneficiary of an annuity currently. I qualify for Social Security. So I receive the same dollar amount every month. That is a stream of equal payments at set periods of time. Once a month, same dollar amount. That's an annuity. I want to show you the tables, even though I want you to use Excel. Let's see, what does Excel access? Embedded in Excel, you have tables like this. This is a future value table. There's an amount colored in gray here on the right-hand side of the box. It's at 4 periods, the intersection of 4 periods and 10%. We have a factor of 1.464. So if I gave you a principal amount of $1,000 and expected you to grow that money at 10% per year for a 4-year time period, you could take that $1,000 and multiply it by this factor, 1.464, and arrive at your answer, which would be $1,464. So these are the details of the tables inside Excel as you might seek to solve for a future value amount. Similarly, we can see a present value table. These tables are in the back of your textbook. They're embedded in financial calculators. They're embedded in Excel formulas. In this case, if we knew that 4 years from now, in a 10% interest rate environment, we were going to receive a sum of money, but we want to know what is that present value today, rather than waiting for 4 years, we would take the future value amount and multiply it by this fraction of 0.683 in order to determine what is the present day value or the present value amount. I want now to shift again to a different slide deck. And in this case, I need to move out to slide 95. So allowing a moment here for that to happen. Let me get deeper into this slide deck. And actually, this is the wrong slide deck. So if you'll wait for a moment, we will go ahead and access the correct slide. I'll share a different slide deck with you at this point. And we'll solve some additional problems. In this case, our problem is stated as follows. Suppose you plan to invest $20,000 in an account paying 8% interest. How much will you have in the account in 15 years? So you're given a present day amount. You're going to grow it into the future. So we're going to likely use the FV function to solve that problem. So access the FV function in Excel. Our rate is 8%, so input 0.08. The numbers of periods in this case are 15 years. And the present value amount is negative $20,000. Input all of those things in the drop-down box you're given in Excel, and you should get the result of $63,443. Our grid work here in the middle of this slide shows us the variables you input into Excel. The rate at 8%, the numbers of periods being 15, the fact that we're solving for future value, and we start with a present day amount of negative $20,000, the result is given as $63,443. This example causes us to determine the value of an annuity. So the word problem reads as follows. Suppose that you invest $20,000 in an account paying 8%. You plan to withdraw $2,000 at the end of every year for 15 years. How much money will you have left in the account after 15 years? This would be solved by accessing the future value function in Excel. Our rate is at 8% or 0.08. The numbers of periods are also 15. We're starting with a present day amount of negative $20,000, but we have a payment in this case. That's the annuity. That's that stream of money each and every period of $2,000. So we input $2,000 in the payment block and solve, and we'll receive the answer of $9,139. What is that? Well, that represents that if we were to begin with $20,000, compounded at 8% for a 15-year time period, meanwhile, we're withdrawing $2,000 per year, we will end up with, at the end of the time period, at the end of the 15 years, a balance of $9,139. Moving to our next example, which in this example, we're dealing with an annuity, but we're going to want to determine the following. You're about to purchase a new car. You have two options. You can either pay $20,000 right now, or we can go out and get a loan. If we get a loan, it's going to be a $500 payment each month. We'll have to make those payments for 48 months. If the interest rate that you're going to have to pay is 1/2 of 1% per month, what is your payment going to be? What is that going to value to? Again, in this case, we're using the present value function, but we have an annuity that we're working with because you have those regular payments of $500 a month for 48 months. That's the annuity. So our periods are 48 periods, or representing the 48 months. The rate is 1/2 of 1% per month. Our payment is $500. If we input all those variables into the drop-down box on the present value function, you will find out that you're given an answer of $21,290. So that's the present day value of making 48 payments at $500 at a rate of 1/2 of 1% per month. We could then use that $21,290, compare that to the $20,000 it would cost you to buy the car outright. We find out the smarter option for you is to pay the $20,000 now, because the value of all those future payments in the future is higher, $21,290, after we have present valued those payments. We're now going to solve for a payment. We could also, with these variables, solve for rate. You would call upon Excel to give you a rate formula. In this case, we're going to call upon Excel to give us a payment formula in order to solve this problem. You're a biotech firm, you want to buy a piece of equipment for 500 grand. The individual or the firm selling this to you requires a 20% purchase price at down payment, willing to finance the remainder at $48 for over 48 months at an interest rate of 1/2%. What's the monthly payment going to be? Using the payment function in Excel, we know we have a monthly rate of 1/2%. We input that in the rate bucket as 1/2%. The numbers of periods are 48. The present value amount is a negative $400,000. We solve. And we find out that we'll have to make monthly payments of $9,394 in order to finance this piece of equipment over a 4-year time period at a rate of 1/2% per month, which annualizes to 6%. Those are the types of problems we can use these time value of money concepts to solve. We can grow money into the future. We can take future money and discount it back to today. We can take annuities, either in the future or the present day, and either grow them or discount them. We can also solve for rate. We can solve for payment. Familiarize yourself with these tools. They are regularly used in the financial industry and drive many, many transactions throughout the world of finance.